So this is on page 30 of your unit handout. The inflection points that we're talking about in this lesson are the same as the inflection points that we talked about in Math 30-1 when we were dealing with polynomial functions. The difference is that those inflection points always occurred on the x-axis. And to remind you of that and what an inflection point looks like, this happened, and this is not going to be the case necessarily with the functions that we look at. But we said that if you had a polynomial function, this is in 30-1, that had x times x minus 3 squared times x plus 4 cubed, we talked about multiplicity and the fact that we have a factor of x in the polynomial. There must be a 0, which means an x-intercept of 0. If we have a factor of x minus 3, there must be an x-intercept at positive 3. And because we have a factor of x plus 4, there must be an x-intercept of negative 4. And I'm just going to move this over. And we said that you could base the sketch of the graph on some properties of polynomial functions. For example, if you were to expand this polynomial function, I could just tell you my point, but I don't want it to be kind of in a vacuum. I want you to understand the whole thing. We could expand it and get x to the 6 plus a whole bunch of stuff. And then we would have, oh my goodness, 64. Well, you would actually have plus 0 for a constant term because of that x in front. But the point is, you would know that since the degree of the polynomial is 6, which is even, and the leading coefficient is positive, the function has a right arm and a left arm that are both up. And then you would sketch it. But you would sketch it by saying that this point here must be an inflection point, because the degree is 3 for that factor. This must be what we call a tangent point. And this, I think the word that I use in Math 30-1 is it's a clean intercept. So what this looks like is when you sketch it, the way I would describe it to you in Math 30-1 is for the tangent point, it's like it's going to go through and it changes its mind. And then for an inflection point, I would say it's like it's going to go through and change its mind, and then it changes its mind again. So what ends up happening is the graph looks something like this. And I want you to focus on this part of the graph where there is an inflection point. There is a more sophisticated way to explain why that's an inflection point. And it has to do with how the graph curves. We're going to get to the details of this in a minute. But I hope you see that to the left of this inflection point, the graph has this kind of upwards curve. And to the right of the inflection point, it has this kind of downward curve. And that's what we call concavity. The concavity of the curve here is different than the concavity here. By the way, the concavity right here is the same as the concavity here. And it's the same as the concavity here. So these sections that I'm going to highlight in black, these all have the same type of concavity. And it has to do with the second derivative. So, remember that when the derivative of a function is positive, then the function is increasing. I want to really break this down for you. The derivative of a function tells you what is happening to the function. So if the derivative of the function is positive, the function is increasing. If the derivative of position is positive, then position is increasing. If the derivative of area is positive, then area is increasing. So a positive derivative tells you the thing that it's the derivative of is going up in value. Similarly, when the derivative of a function is negative, then the function is decreasing. And again, I want to highlight for you here, it's the derivative of the function. So it's the function whose description we can talk about. If the function has a positive derivative, the function is increasing. I know I've repeated myself upwards of 8 times there, but it's very important. So what that means is that if the derivative of a function tells us what the function is doing, then the second derivative tells us what the first derivative is doing. Just let that sink in. I can give you a flow chart here in terms of differentiation. You differentiate with respect to x, y to get dy dx. So dy dx tells you what is happening to y. If you differentiate again with respect to x, you get the second derivative. So that must mean if the first derivative tells you what y is doing, then the second derivative tells you what the first derivative is doing. And this is very tricky. It's not easy on the brain. And the first derivative is slope. So just a second here. Go back to this. I'm going to write the word slope here underneath first derivative. This is the slope of the graph. So if the second derivative is telling you what the first derivative is doing, the second derivative is telling you what the slope is doing. And that, in and of itself, is a very tricky thing to wrap your head around. What does it mean? What do you see on a graph if the slope is increasing? What do you see on a graph if the slope is decreasing? Well, you see 2 different types of concavity. So, if the second derivative of a function is positive in a particular interval, then the slope must be increasing, because the second derivative is telling you what's happening to the first derivative, and the first derivative is slope. So the second derivative is telling you what's happening to the slope. And if the second derivative is positive, the slope is increasing. Well, if you have an increasing slope, it looks like this, generally speaking. It has this upward bow to it, which is called concave up. F double prime of x is greater than 0 whenever the graph looks like that. Concave up can be recognized because if this were put out in the rain, it would fill up with water. The water wouldn't drain off of it, you would collect water. By the way, this greater than 0 means positive. And I don't know where I picked this up, but some people do have difficulty with shapes. I hope you would agree that somebody who is positive, generally speaking, is happy. They are smiling. And that's one way that you can remember that that shape has to do with a positive first derivative. Let's break this down a bit though. I told you that a second derivative being positive means the slope of the function is increasing. And I'm talking about increasing from left to right. So let's demonstrate that to be the case. If I take a look at a number of points on this function that I've drawn, just take point A. I hope you would agree that if I looked at the slope of the tangent there, I wouldn't be out of line by saying the slope of the tangent is -3. These are just hypothetical values, but I hope you would agree that that slope tangent line could have a value of -3. If I take a look at a point next to it, it still has a negative slope, but it's not as severe. Again, if this has a slope of -3, I don't think I would be out of line in saying this has a slope of -2. It's still negative, but it's not as I said, severe. If you take a look at another point, C, it still has a negative slope, but it's pretty meek. It's pretty mild, about negative 0.5. And the slope at D, I hope you would agree, is 0, because that would be a minimum where the slope of the tangent is horizontal. And the slope at E might be 0.5, and the slope at F might be 0.8. I think those numbers make sense to you. But if you take a look at what happens when you go from A to B, you're going from a slope of negative 3 to negative 2, and that is an increase. Which is more, negative $300 or negative $200? Negative $200 is more. It's still not great, but it's more or better off than negative 300. When you go from negative 2 to negative 0.5, that's an increase. Negative 0.5 to 0, that's an increase. 0 to 0.5 increase, 0.5 to 0.8. These are all increasing slopes. And since the slope is increasing and the slope is the derivative is increasing. And if the derivative is increasing, the second derivative is positive. What I'm doing here with this is I'm trying to get you to understand why the second derivative positive creates a concave up shape. If the second derivative of the function is negative, then the slope must be decreasing, and it turns out that that is called a concave down shape. And again, the same kind of thing, if you want and need something to help you remember, that if you see somebody walking down the street and they look like this, generally speaking, they're not unhappy, they're negative. You know, it may be intentional, it may be just incidental, but at that point in time, they are in a negative mood. Briefly here to demonstrate this to you, the same kind of thing. I'm going to pick a number of points. Well, I'll back up. I don't want to rush through this. Point A might have a slope of 3. Point B still has a positive slope, but it's not nearly as steep, maybe 2.5. C might be 1.5. D has a slope of 0. E has a slope that's negative, maybe negative 0.5. And F is maybe negative 0.8. All of these numbers, when you go from left to right, from A to B to C to D to E to F, the slopes of the points are decreasing. They're getting smaller. That's a decrease. This is a decrease. That's a decrease. That's a decrease. And that's a decrease. So the conclusion that we draw is concave up has that upward shape, concave down has that downward shape. When I started this lesson off, I talked about inflection points in terms of Math 30-1. So this section right here would have a dy dx that's positive. This section in here would have a dy dx that's negative. And the other comment I would make is in 30-1, all of the questions are designed so that those inflection points are on the x-axis, but the x-axis could be here. And it doesn't change the fact that it has to do with the second derivative. All right, so a point where the concavity changes, where the function goes from being smiley happy face to sad frowny face, in between those two regions, it's neither concave up nor concave down, and that's what we call an inflection point. In 30-1, I would just call it some kind of a wrinkle or a twist. So at an inflection point, the graph is neither concave up nor concave down. But just a second. Concave up has a second derivative that's positive, and concave down has a second derivative that's negative. So at an inflection point, if it's not concave down and it's not concave up, then the second derivative cannot be positive and it cannot be negative. Well, what are the only other possibilities? The second derivative at that point must either be equal to 0 or not defined. Just like a max-min must have a first derivative that's either equal to 0 or undefined. Just like with max-mins, if you find all of the points that make the derivative, not the second derivative, because I'm talking about max-mins, with max-mins, if you find all of the points where the derivative is equal to 0 or undefined, some of them may be max-mins, some may not. The same is true for second derivatives and inflection points. The points where the second derivative is 0 or not defined might be inflection points, but they might not be. And we call those points critical values of x for the second derivative. So if you are interested in max-mins, try to break this down. If you're thinking here about max-mins, then you find the critical values of x by asking where does the derivative equal 0 or where does the derivative give an undefined value. But all of these values that are critical for the first derivative may or may not be max-mins. Okay, so if you're thinking here, I want to explore a function and determine the inflection points, then you find the critical values, but it will be for the second derivative. And you get some critical values. These may or may not be inflection points. So going to the left of your screen, how do you determine which of those critical values correspond to max-mins? Well, you do a first derivative table. You do a first derivative chart. So how are you going to determine which of these critical points on the right are inflection points? You're going to have to do a second derivative table. And that's what we're working on today. I'm going to pause there. Any questions about concavity or inflection points as it relates to the second derivative? All right. So for each of the following, determine all pertinent features of the function, including the new stuff today. And you may need an additional sheet of paper for your work depending on how you organize it or how big you write. So we have a function f of x equals x over x squared plus 1. Let's determine the symmetry first. So how do we do that? I'm curious how many of you know what the symmetry is by looking at that function. Can you type in the chat window of Google Meet what you believe the symmetry is, whether it's odd, even, or neither, if you know? Yeah, it's odd. I would probably, if I were doing this on my own, just write odd. If I were doing this because I was going to be marked, I would do f of negative x, and I would put negative x everywhere in the function where there's an x, and I end up with f of negative x equals negative x over x squared plus 1. And this is f of negative x is equal to negative 1 times x over x squared plus 1. But this is f of x. So f of negative x is negative 1 times f of x, which means it's odd. I'll be honest with you. I think that piece of information is the least helpful in getting a sketch of a function. It's certainly something we can look at later on and say, oh yeah, that makes sense, it's odd. Let's do intercepts, x-intercepts if there are any, and y-intercept. Well, since there's a factor of x in the numerator, that means that x equals 0 is the x-intercept. And by the way, there are no other factors. It's not like x times x plus 1. If it were x times x plus 1 in the numerator, then negative 1 would also be an x-intercept. Y-intercept is found by replacing every x in the function with 0. So we would get 0 over 1, which is 0, which makes sense because if the graph crosses the x-axis at 0, it has to go through the origin. And that means it has to have a y-intercept of 0. Vertical asymptotes. Well, that's where we look at the denominator and we ask ourselves, and I don't know that you need to write this down, but you ask yourselves, what value of x makes the denominator 0? And you just stare at it all day. There's no value of x that's going to make that equal to 0. So there's no vertical asymptote. Horizontal asymptote will be y equals 0. Now, I'm using the shortcut, and I really don't think there's anything wrong with using the shortcut. If it were written response, you can't do that, but the degree on the top is 1, the degree on the bottom is 2, so the degree on the top is smaller. If you want to do it properly, the location of the horizontal asymptote is the limit as x approaches infinity of x over x squared plus 1, and this is where we divide every term by the highest degree term. The top of this expression will turn into 1 over x, which at, I guess I'll write it down. So this limit is going to be equal to the limit as x approaches infinity of 1 over x over 1 plus 1 over x squared. At infinity, this is 0, and this piece of the bottom is 0, which means you're left with 0 over 1 plus 0, which is 0 over 1, which is 0. So what we've got on this first screen here, and on the right is kind of some of my, a little bit of scrap work, but what we have to the left of this line is the little bits and pieces of the function. We know the x-intercepts, we know all about the asymptotes, we know it's odd. The heart, the meat of this matter is going to be in the first and second derivatives. So we need to take y equals x over x squared plus 1 and find the first derivative. Why are we finding the first derivative? So we can do a first derivative table, which will allow us to know where the function is increasing, where the function is decreasing, and where potential max-mins are. And I take that back. Once we do the table, we will know where the max-mins are. Derivative of the top, we're going to use the quotient rule times the bottom, minus the top times the derivative of the bottom over the bottom squared. So my derivative is, I won't cut any corners here, x squared plus 1 minus 2x squared over x squared plus 1 quantity squared. Here's my derivative in clean form. 1 minus x squared over x squared plus 1 squared. Critical values would be plus 1 and minus 1. Well, let's do our first derivative table then. My first derivative table is going to have an interval from negative infinity up to the first critical number, which is negative 1. So when you put these on a number line, the negative 1 comes first, then from negative 1 to 1, then from 1 to infinity. And across the top, well, there's a lot of ways to do this. I might have to just move something to give myself a little bit more space. Oops. Actually, we'll just move it back. I'll just write small. Across the top, what we have is 1 plus x, 1 minus x, and then x squared plus 1 quantity squared. Be careful here because it's 1 plus x and 1 minus x as opposed to x plus 1 and x minus 1, which part of that would be different. This will be negative then positive. If I put in a number in this interval like negative 20, 1 plus negative 20 is negative. If I put in a number in this interval like 0, 1 plus 0 is positive, and then it continues to be positive. 1 minus x is positive in this interval, positive in this interval, and then it becomes negative here. And the third one is positive everywhere because of the squared. What does that tell us? It tells us that the derivative is negative, then positive, then negative. What does that tell us? I almost didn't give myself enough room, but I'm going to squeak it in. It tells us that the function is decreasing, then increasing, then decreasing. Which means that at negative 1 there's a minimum, and at positive 1 there's a maximum, which makes sense. The thing is odd. We do have to have some kind of symmetry here. So I'm going to go back to where I've compiled the pertinent information, and I'm going to add that to our list. We've got a minimum at negative 1 comma something, and we have a maximum at positive 1 comma something. And while I'm here, I might as well use the function to determine the y coordinate. I'm going to write this in a different color because I'm going to erase it in just a second, but the original function was y equals x over x squared plus 1. So if I put negative 1 in there, the top becomes negative 1, the bottom becomes negative 1 quantity squared, which is 1, plus 1, the bottom becomes 2. So the y coordinate when x is negative 1 is negative 1/2, which means, everybody, I don't even need to look at doing the same thing for the y coordinate at 1, because the function's odd. If the function's odd, then the y coordinates at negative 1 and positive 1 are going to be opposite. So we've got more information added to our list. Any questions with calculating the coordinates of the max mins or with our first derivative or first derivative table? All right then, We are going to now take our second derivative, or sorry, our first derivative, dy dx, which is 1 minus x squared over x squared plus 1 squared, and we're going to differentiate it to determine the second derivative. d2y dx squared is how we write the second derivative, and I'm still going to have to use the quotient rule. The derivative of the top multiplied by the bottom minus the top times the derivative of the bottom over the bottom squared. And again, it would be, I think, a fatal mistake. Not necessarily, but sooner or later it's going to be a fatal mistake if you don't stop and just double check everything. So I'm speaking as I'm double checking it because it's just the way my mind works when I'm teaching, but you need to double check all of this as well. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared, which would make this a power of 4. What you're going to do now is factor the numerator. Just looking at this, my immediate reaction is to factor the negative out. I can see that we're going to end up not regretting, but deciding that it would have been better if we didn't. But I don't think most people would see that. I'm going to take out a negative 2x, and both of these terms, again, just to show you visually, we're talking about here this term minus this term. Both of those terms contain an x squared plus 1. One of them is squared, one is to the 1, so I can write x squared plus 1. What do I have left out of the first term? I have an x squared plus 1. No need to put brackets around it, but I could if you like. That would give us the x squared plus 1 quantity squared in the first term. Then I took out a 2x. I still have a 2. I have this 2. I took this 2x out. I still have that 2. I factored out the negative. I factored out the x squared plus 1. So I have 1 minus x squared. Over x squared plus 1 to the 4. Double check that. I took out the negative 2x. I took out the x squared plus 1 to the 1. Out of the first term, I will have left x squared plus 1 to the 1. Out of the second, I will have a 2 and a 1 minus x squared. By the way, you want to, with these questions, and this is kind of what we're working on for the rest of the week, like really take your time. If your second derivative chart has an error in it, you're going to go nuts trying to figure out what the graph looks like if your first derivative chart is correct and your second is incorrect. It's already tough enough. Let's see, d2y dx squared will be negative 2x. I'm going to take that x squared plus 1 to the 1 on the top and reduce it with one of the x squared plus 1's on the bottom to give x squared plus 1 cubed. And then I would probably want to do this next part in one step, but after saying take your time and be careful, we want to be very careful. So all I'm doing is multiplying that 2 through, and what I end up with is the second derivative equals negative 2x times 3 minus x squared. Yeah, it's kind of what I thought. I want to take that negative out to begin with because there's just negatives everywhere. But I see that it would be better for me at this point to take this negative and throw it back inside, and that way I'm not dealing with as many negatives. So my second derivative is d2y dx squared equals 2x times x minus 3, my mistake, x squared minus 3 over x squared plus 1 squared. Any questions with those last couple of steps? Cubed. Thank you, David. Definitely cubed. All right, so now what we're going to do, just want to clean that up a little bit. Now what we're going to do is identify our critical values of x for the second derivative. And we have 0 because of the factor of 2x in the numerator. We have plus or minus root 3 because if you take x squared minus 3 and set it equal to 0, and I'm not going to include this as part of your work, but if you solve this, you have two options, and one is to move the 3 over and then go plus or minus root 3. The other option, though, is what I would prefer us to do because it's going to be helpful in our chart. Factor x squared minus 3 into root x plus 3. Sorry, into x plus root 3, x minus root 3. And then you can see the solutions. And that will be important because then I can put in linear. They're not really linear, but I don't have to put in a quadratic. I guess they are linear. I don't have to put in x squared minus 3 in my second derivative table, which is troublesome if I do. So these are my critical values of x for my second derivative, which means we're going to go from negative infinity to negative root 3, from negative root 3 to 0, from 0 to root 3, and from root 3 to positive infinity. Across the top, we are going to have, I'm looking here. I'm not looking at the line above it. Across the top, I'm going to have 2x, x plus root 3, x minus root 3, x squared plus 1 cubed, my second derivative, and what it's telling me about the function. All right, here we go. Negative infinity to negative root 3, negative root 3 to 0, 0 to root 3, and root 3 to infinity. I'm really glad that we went with this second derivative as opposed to the one above it. Dealing with that negative and everything else being opposite for the linear factors would be troublesome. 2x is negative whenever x is negative. 2x is positive whenever x is positive. X plus root 3 will be negative until it passes the 0 of that factor. So before negative root 3, x plus root 3 is negative. After negative root 3, x plus root 3 is positive. The same thing will be true with x minus root 3. It will be negative until it passes the 0 of that factor. Now, x squared plus 1 quantity cubed is going to be positive everywhere because x squared is always positive, and when I add 1 to anything that's positive, it will be positive, and when I cube anything that's positive, it will be positive. So what does that tell us? If we multiply this out, negative, negative, negative times positive gives you negative for the second derivative. In the next interval, it's positive for the second derivative. Then it's negative for the second derivative. Then it's positive for the second derivative. I'm going to pause for a second, and before I ask if you have any specific questions, I need to know if I'm going too fast, too slow, or just right. If I'm going too slow, quite frankly, that's fine. Okay. So what does that tell us? If this were a first derivative chart, please don't write this down. If this were a first derivative chart, you'd be doing this. But it's not a first derivative chart. It's a second derivative chart. What is y, which is the graph, doing when the second derivative is negative? It looks like this. And when the second derivative is positive, it's concave up. And when it's negative, it's concave down. And when it's positive, it's concave up. So let's just stop for a second. That means that the function before negative root 3, on this side of negative root 3, the graph is concave down, and then on the other side of negative root 3, it's concave up, which means the concavity changes. So if the concavity goes from concave down to concave up, there's an inflection point. And in fact, since the concavity changes at each of these three critical values, the concavity goes from negative to positive across root 3, positive to negative across 0, negative to positive across root 3, we have 3 inflection points. And we need to add that to our list of information. We've got our symmetry, we've got our x-intercepts, we have all of the information about the asymptotes, we have max-mins. Now what we have is inflection points. We have inflection points. 3 of them. 1 at negative root 3, comma something. 1 at 0, comma 0. I know the y-coordinate of that point because that's the origin, and we knew that the graph went through the origin. There was an x and y intercept there. We also have at positive root 3. Since the function was odd, these two numbers, these two y-coordinates for the inflection points must be opposite at negative root 3 and positive root 3. Remember, it's hard to believe this is still example 1, where this was the function. Double check that. Yep. So what we need to do is figure out what the y-coordinate is when x is negative root 3. So it's negative root 3 over negative root 3 quantity squared plus 1, which is negative root 3 over 3 plus 1. Because when I square the square root of 3, I get 3, and I'm squaring a negative, so it becomes positive. So it's negative root 3 over 4. I don't think we need to do that again. Since the function is odd, we're simply going to switch the sign because x switched. By the way, this is what I meant when I said the symmetry is maybe some of the least useful information. The only place I really find a use for it is taking shortcuts and finding y-coordinates. So now we're ready to graph this. And after we graph this, we're going to take about a 10-minute break because the next example is going to be demanding as well. And essentially, we're going to get through the second example today after our 10-minute break. Then tomorrow, we're going to be working on some of these. And the day after that, we'll move on, I think. That's my plan anyway. This is pretty intellectually taxing. It's hard work. It makes you tired. So, how are we going to graph these? Well, we have a whole lot of information. I would like you to construct, you can use a ruler if you like, but if you got a steady hand, a set of axes, and I want you at the top to put some horizontal line which mimics the x-axis, and you're going to leave some space in between those two. We can start adding some information to this. We know that the x-axis is a horizontal asymptote. We also know, I'm going to graph the function in blue so it's maybe a little more visible. We also know that the graph passes through the origin. Now, look at, what I'm asking you to do right now is to look at the values of x that were important in our analysis. Look at the critical values of x for your first derivative and for your second derivative. And things happened for your first derivative at +1 and -1. Those were the only two critical values. So something important happens at 1 and -1. We're going to have to scale the graph so we can see at x equals 1 and -1. But before we do, were there any other important x coordinates? Well, yeah, the second derivative, I need somebody to verify that my memory is right here, but your second derivative had 3 critical values of x, 0, √3, and -√3, correct? Okay, good. So up here, I'm just writing some stuff in the top right corner so I can refer to it, but I believe -√3 is approximately, I want to just fix that. I believe -√3 is approximately -1.7, I think. Yay or nay? Okay. And, okay, so we have something happening at 1, at -1, at -1.7 and +1.7. I'm thinking that when I scale this, I'll probably want to go 1, 2, maybe up to 3. 1, 2, maybe up to 3. So on the x-axis, I've scaled these so that I'll just put in -2 here, whoops, +2 here, and -2 here. So as long as I've got all of the horizontal key numbers visible on my axes, I'm ready to go. Now what I'm also going to do at the top is mark off my critical values of x for the first derivative. Those are critical for the first derivative. We'll come back to that in a second. Let's finish our scaling. What were our y coordinates? Well, we had, and again, correct me if I'm wrong, we had a min at -1, -1/2, and we had a max at +1, +1/2. Can I get a yes on that? Okay, good. So I need to scale things vertically to get to -1/2 and +1/2. I also had, and this is just me talking and using scrap paper here, we also had inflection points at -√3, -√3/4. Is that an inflection point? Yes? Okay. What is the value of -√3/4? I think it's going to be around 0.4 something. 0.43. Okay, so I need to, this is about -0.43. I need to scale things vertically so that I can hit negative 1/2, positive 1/2, and negative 0.43, positive 0.43. I'm thinking this. There's nothing else that happens outside of that range of values of y. So now let's plot, oh, and by the way, one other thing. Let's label up on our horizontal line. No, I'm going to save that. Okay, so let's plot these points. Negative 1, comma, negative 1/2 is about here, and that is a minimum. Positive 1, positive 1/2 is about here. I talked about this when we talked about symmetry and graphing before. If you were to connect these 3 blue points, they should form a nice straight line if you've scaled things properly. Okay, what about the inflection point? So I'm going to use different colors here. Negative root 3 is about here. And I'm going to mark that off at the top. So this is a critical number for the second derivative. There's another critical number for the second derivative at positive root 3. I'm going to mark that up here. And there's another critical number for the second derivative at 0. So what I've got at the top in green are my locations horizontally of my second derivative's critical numbers. And what I have in red are my locations of my critical numbers for my first derivative. Okay, let's plot these inflection points in. I'm going to write this down again just to confirm that this was an inflection point, which is about negative 1.7, comma, negative 0.43. I'm just asking for one more confirmation on those numbers. Okay, so where does that point lie? Well, at negative 1.7, that's where the green mark is on the axis. Negative 0.43 is like not quite as low as negative 1/2. I mean, it's close. And then over at positive root 3, we're going to have positive 0.43. Now again, I don't know, if I wanted to check this and I were doing this on paper, I would literally take out a ruler. I would put my ruler down here. That's pretty close. If I wanted to really check it, I would measure the distance from that point on the left to the origin, and I would measure the distance from the origin to the point on the right. I could have done a better job scaling, but it's not bad. Okay, so now, what I'm going to put at the top is the following. I'm going to put arrows for my first derivative. When I go to my first derivative table, you're going to be looking right now at your first derivative table and listening to what I'm saying. In your first derivative table, the function is decreasing from negative infinity to negative 1, which means that the function goes down, 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 down. Notice it goes down through that green critical value for my second derivative, because that green critical value has nothing to do with increasing or decreasing. The function is increasing, your second derivative is positive, everywhere from negative 1 to 1, and then it's negative afterwards. So whatever you draw has to be increasing to the left of this point, decreasing from that point to this point. Sorry, let me start again. Whatever you draw has to be decreasing to the left of this, then increasing from there to here, then decreasing afterwards. What about your second derivative? Well, your second derivative, in your first interval, I'm going by memory, I need some help here. In your second derivative, the first interval from negative infinity to negative root 3 is negative, correct? Okay, so that means, and here's your first negative root 3 critical point. The function is concave down, and then it becomes concave up to 0, and then it becomes concave down to positive root 3, and then it's concave up afterwards. So your challenge right now, and I'm going to give you a minute to do it, is to sketch a function that has all of those properties. And to type into chat, got it, or I think so, if you do think you have what it looks like. And we're trying to be honest here, you're not cheating by looking at a graphing calculator. And while you're still thinking, I don't mean to distract you, but this is a perfect example of a midterm exam question in post-secondary calculus. Problem number 2. Sketch a detailed graph of y equals x over x squared plus 1, showing all asymptotes, intercepts, concavity, etc. And you don't have a graphing calculator, you don't even have a calculator sometimes. So if you break this down, we're always talking about thinking about horizontally. So everywhere to the left of there, look up at the top, the function has to be decreasing and concave down. Well, I'm gonna sketch something here in pieces, and it's not gonna look good, and then I will sketch the way it should. What some people will do then is they will say, well, the only way to sketch something that is decreasing and concave down is to sketch that. And that's good. And then from that point to this point, something changes at this point as well. What changes is it still decreases to that point, and now it's concave up, but then it changes at that point to being increasing. So what does it look like here? Well, it looks like that. Now, this is the, not like that. That's no good. I was trying to exaggerate something. It looks like that. And you know what? I did not bad. I want everybody to focus here on this area. Do you see that that transition is smooth? I hope. What you don't want to do is end up drawing something like this. Oh, concave down and decreasing, concave down, and you don't want it to have points to it. So when you put this all together, you're going to get a nice smooth curve that looks like this. Concave down, decreasing, all of a sudden becomes concave up and decreasing, concave up and increasing, concave down and increasing, concave down and decreasing, concave up and decreasing. It looks like that, and it's asymptotic. And that's really pretty good. Like, I'm impressed. It looks good. If we take a look on our graphing calculator, what did we have? X over brackets x squared plus 1, end bracket. Let me scale it to the same window settings I have here from -3 to 3. We go from 1 to 1? Sure. -1 to 1. It's not nearly as tightly asymptotic around 3 as we've drawn it. It's maybe more like this, but man, that's pretty good. So it's pretty impressive that what we have is the ability to bypass our graphing calculator. You can get a nice picture of this thing.